The first concept we need to understand in our exploration of energy is work. Now, work is another one of these words that we use in physics with a different technical definition than that word has in everyday language. So, in physics, we have a quantity work that can be defined. Well, I'll show you the formula in just a second. Let me show you the situation it applies to. Let's say we have a box and we're pulling that box across the floor with some force, and that force is applied at an angle theta with respect to the horizontal. The work that we do on that box, the work done by the force on the box, is defined as the magnitude of the force times the magnitude of the displacement, how far the box travels, times the cosine of the angle between the force and displacement vectors. Now, first thing to point out about this definition is that unfortunately we're using the letter W again for something completely different. Up till now we've been using W for weight or gravity force. Now the symbol W has an entirely different application. It's used to symbolize work. I didn't invent this notation. I'm sorry if that's confusing. You have to know from the context of the problem which W we're talking about. So W now in Unit 5 represents work, and the work on this box equals the force applied to it times the distance it travels times the angle between the force vector and the displacement vector. So let me point out that theta is not always measured from the horizontal. Theta is measured between F vector and delta X vector. Okay, so with this definition in mind, let's look at several examples to understand how we use this definition. So example 1, let's say you lift a bucket of water off the ground. You lift it at a height of 1 meter above the ground. Maybe that bucket has a mass of 10 kilograms. So let's calculate how much work you need to do. And one more important thing to say is that you lift it at constant speed. So the bucket's not accelerating. That means that the force that you apply to the bucket will equal the bucket's weight. That way it'll travel at constant speed and it won't accelerate. So the applied force in this case will be just the weight of the bucket, and I'm being careful not to write W for weight just because we'll get really confused, so I'll write mg instead. And that's going to equal 10 kilograms times 9.8 meters per second squared, or 98 newtons. 98 newtons. And that distance is 1 meter. And if you think about the situation where you're pulling the bucket upward, that means that you're applying a force in the upward direction on that bucket, and the displacement of the bucket, because it's moving up, is in the same direction as that force. So you pull up, force vector points up, bucket moves up, displacement vector points up, and so since theta is between F and delta x, that means theta is 0 degrees. They're parallel. So you find that the work done on that bucket of water is F delta x cosine theta, or 98 newtons times 1 meter times cosine of 0, which is 1, or 98 newtons times meters. That would also be kilograms meters squared per second squared. We're going to learn another name for that unit soon. Now let's look at a second example. Let's say now we've lifted that bucket off the ground, and now we walk with it, we carry it, just horizontally. Maybe we walk 5 meters with that bucket of water. This time, we're still applying an upward force to hold that bucket up and counteract gravity. But the displacement vector is horizontal, because the bucket is moving horizontally as we walk. And you can see from this picture that the angle in the problem this time would be 90 degrees. So that means that the work you do equals 0, because cosine of 90 is 0. And this is really where the physics definition of work is completely different from your everyday definition of work. Because in real life, if you're carrying a heavy bucket of water, you're like, I'm doing a lot of work carrying this water around. But according to physics, in our definition of work, you are doing 0 work, as long as the force and the displacement are perpendicular to each other. 0 work is done. And we're going to learn that the reason why we define work in this way is because when the force is in the direction of the displacement, then the object's speed changes and its kinetic energy changes. Let's look at a third example now. We've picked the bucket up, we've walked around with it a little bit, and now we need to set it down. So let's lower it to the floor at a constant speed. So once again, there's no acceleration, and the force you apply still equals the bucket's weight. As you lower it to the floor, you still have to pull upward on it for it to go at a constant speed. So the force you apply is still upward, but now, because it's getting lowered down, the displacement vector points downward. So force and displacement are now opposite to one another, and the work done on the bucket is our same force of 98 newtons at displacement of 1 meter. But now the angle between F and delta X is 180 degrees because they are anti-parallel to one another. And that equals -1. So we get negative 98 Newton meters of work done. So by picking the bucket up, you've done positive work on it. By walking around horizontally, you do 0 work. By setting the bucket down, you do negative work on that bucket. Now let me do one more calculation. This is an example from your textbook. Let's say that you're pulling this object and it has a mass of 50 kilograms. Let's call it a sled this time, because in your textbook they do an example of a sled with some fish on it. And you pull with an applied force of 120 newtons at an angle of 30 degrees for a distance of 5 meters. Calculate the work done on that sled that you're pulling. All you got to do is plug into this formula. Turns out that mass was kind of irrelevant to do this calculation. All you need is a force, 120 newtons, displacement of 5 meters, and the problem tells you that the angle between the force vector and displacement vector is 30 degrees. That'll give you a value of 520 newtons times meters, and now I'll introduce the new name for that unit, that combination of units. When we have newtons times meters, that's the same thing as kilograms meters squared per second squared. And in honor of scientists, we call that joules. With the symbol capital J.